Um, Hello, good morning to everyone. It's a pleasure to introduce you to Dr. Ioannis Liritzis. Dr. Ioannis Liritzis is a distinguished professor of natural science in cultural heritage at the archaeological environment at Hainan University at the present in China. He is currently the vice president of the European Academy of Science and Arts in Salzburg. He's being awarded with many honorary awards, and he's currently doing some interesting projects, which include the Obsidian dating studies. Mostly, he's trying to develop some AI in archaeology and apply science and technology and engineering in arts and culture. He's involved in education, research, and innovation. He's been awarded he has honorary titles from the Northwestern Polytechnic University of China, South China University of Technology, Samara State Institute of Culture in Russia, and he's a corresponding member academic of the Sciences et Arts et des Lettres de Dijon. I think I pronounce French quite properly, but anyway. It's a pleasure to introduce his talk about recent advances in the Obsidian hybridization dating. We are very happy to have it. Thank you very much.
Thank you, sir. Thank you. I don't forget our very harmonic collaboration we had in this joint paper on the metal fight from China, and we had a very good job. And I think that was the point that we started knowing each other through our friend Stavros Nikolopoulos. That was a triggering that helped us to be again in the forefront of research. And on the occasion that I'm here in Barcelona for another reason, the European Academy is the ceremony as a new member. It was very kind of you to invite me to give a lecture which is related to the subjects that your department deals with, because as you have noticed, my archaeometric applications run from AI mathematics in archaeology to archaeoastronomy, etc. So this time the Obsidian belongs to the geological sciences, geosciences, and I have been involved in this for the last 25 years. I will try to give you the content. So
No, you check.
No, should be there. The content of my talk will be Obsidian tools, chemistry, and surface. Some words about the diffusion mechanism, the water diffusing, entering the obsidian, what is the hydration rim and how we calculate this rim by the various devices. Then fractal dimension of hydration layer. It's a recent work being involved, and the dating methods, the old one and the new that I have developed recently. While everybody, I suppose, know the use of obsidian, the black gold, as they call it, of prehistory, for various everyday practices, and especially before the coming of the metals, which is in the end of 4th millennium BC, 3000, 3300. But even though some societies, they used obsidian blades even later in the 2nd millennium BC, all we know how it is produced from a volcanic lava and fast freezing, cooling down, and produce this glass, which has a degree of crystallinity anyway. Some quartz, feldspar, biotite, etc. but the 90% is glass, international glass, with a low water content, 0.1 to 1% at maximum, which we call pristine water, and high viscosity as well, and high silica content. This views, of Obsidian tools from America and other places. It is interesting to see that the surface of Obsidian, although it looks smooth, it's not so smooth. It has bumps, and concaves. And this plays a great role when one tries to do analysis using secondary iron mass spectrometry. And also this inhomogeneity or irregularity rather of the surface plays a great role in the age calculation, the errors that are involved when we are using ion bombardment of the surface in order to calculate, to define the water content as a function of depth. You can see here the white layer, which is the hydration layer. This is the internal of the obsidian, and the white crystallines are feldspar quartz biotype, etc. Also, there is some atomic force microscopy mapping in order to see the surface irregularities, which play a great role in the as errors, induce errors in the calculation of the age. The attached errors, they increase somehow, the overall error of the age. I will explain you later why, especially using the secondary iron mass spectrometry surface saturation synthesis technique, which I have developed 25 years ago. You can see here the surface of the obsidian. It's like, looks like a cloud. When we fly with an airplane, you can see this kind of pictures, which, for example, you can hear if this line is 8 around microns. By 8 microns, these bumps here would be in the scale of nanometers. For example, here is 500 nanometers. This one here. Other topographic images of various obsidian sources located in a smoother surface in order to bombard with cesium ions, in order to find the S-line curve of water as a function of depth. You can see here, what's going on in the surface, cracks and voids. And also, an interesting thing is that has been found in planet Mars recently, if you know, apart of the water, Indeed, it has been, apart from water, aurora borealis, and water, which is also found, which is terrestrial somehow, things. Our red planet also has ice and water, and aurora. It is very small scale, the aurora, or due to the small magnetic field, but still there. And recently, the last 10 years, has been found also glass obsidian, which has a high content of iron. That is the difference with the terrestrial, which terrestrial is a few percent of iron oxide. Here is more, 20, 30, 35, percent of iron. You can see here some mapping of Mars, with the Mars Express, near IR features associated with the basaltic rock, and the red one, which is associated with the iron-rich glass. Let's see here, the red one and the blue one, or blue, which is basaltic. So one could say that indeed we may say that this is an emergence and archaeology of fluid planets. So whatever studies have been made on the terrestrial obsidian, take into account the high iron in Mars, we may one day be able to apply these experiments and measurements for various reasons of the episode, not only dating, but other reasons as well, in planetary obsidian. So the composition, as I said, is mostly silica, 75%, 1 to 5%, as I said, a few percent of iron, while in Mars is 30%. Here is the diffused water, absorbed water outside in the soil, and here is the unaltered inside the obsidian body, and up to here is the water which has been absorbed throughout the burial period of this obsidian blade. Initial water exists here in the unaltered obsidian, which, as I said, is 0.1 to 0.9% maximum, depends from the obsidian source. And here is the diffused water. And this is the layer that is of dating purposes. We have, as the time passes and we have a temperature, in a place, certain temperature, average temperature, effective hydration temperature, I would say. Then the water from the molecule of water from the surface penetrate into the obsidian with a diffusion rate, the diffusion coefficient, which differs from place to place, depends from temperature, from humidity, from the structure of the obsidian, from the chemistry. So this is a schematic diagram of the unaltered glass, the diffused water glass of obsidian in the first few microns from the surface of obsidian, and this is the outside, the water molecules that are concentrated, and the driving force of water molecules into the obsidian is the concentration of water molecules. Now, let us say a few words about the diffusion mechanism. Well, it has been proposed, the diffusion reaction model by Doremus. The water in the burial environments will interacting chemically with silica oxygen silica clusters produces this equation, okay, with the silanol SiOH groups. Additional research revealed that water molecules in the obsidian surface are the primary molecules that disperse in the obsidian, making hydroxyls and water molecules, and this can be measured by FTIR as peaks, as an amount of water in this hydration layer by FTIR. So the FTIR does not record the profile of water as a function of depth, but produces the total water or total OH in this hydration layer. Also, as a result of diffusion, hydration has a very high surface concentration, while when the diffusion coefficient decreases, high surface concentration and decrease of diffusion coefficient. And also, following my technique, SIMS-SS, it starts, as I said at the beginning, but I repeat here, secondary ion mass spectrometry, surface saturation layer which is a layer nearby to the very close to the surface of the obsidian. That is actually the innovative concept of the existence of this surface saturation that we based our new dating method by SIMS and not by microscope. So I have proposed that this change may be due to the glass surface relaxation when the tension in the near surface region is released. Here is a better picture to understand what is going on. Here again is the obsidian, the interior obsidian. This is the outside, the exterior. This is the surface, atoms per se, and this is here from here the ring, and there two parallel lines you can see the surface and the front of the water going into the obsidian. So this width is the rim or reed or hydration layer, and the SIMS profile is given by this picture. So this is the high concentration in the beginning, going down, and then with an inflection point goes again here in follows, and this relaxation and reduction of the concentration follows the fixed law. So it can give you, the end of the water front with accuracy. And this is the curve that we try to mathematically describe. And this curve includes the time that a molecule ancient time started to enter for first time in the obsidian until this molecule is found, to be somewhere there, himself there. So the time takes from here to there, it is the time, the age of the obsidian until from the time it was used in ancient time by prehistoric people until the time, the moment that we find. The diffusion-based phenomenon is not so easily understood. There are some various theories, what is going on. Is greatly influenced by temperature. So for the same time, an obsidian in Africa or an obsidian in Southern Europe will give different rim width, because higher the temperature, the deeper the water goes into the obsidian. Lower temperature, in a very shorter, interval goes into the computer. So it's very much temperature dependent. Let us see about the hydration layer. This is again the hydration layer schematically from the surface until it falls down. And this is the today, for example, if we are trying to date the material, the diffusion, the water that has been diffused has reached 4 microns. If we find this, if we leave this material, this artifact another, say, 1,000 years, then we could get a similar curve somehow, but would be like that here. Would be to see this drop detail would be 6 or 7 microns in the future. And the surface saturation appears somewhere there, where we have a little flat area of concentration. And then because of the many molecules pushing, what are in front of them, they start, producing this kind of concentration drop. But always there is the surface concentration constant there, which is a very susceptible point that we have to define, because in the age equation we have to define this concentration in the surface concentration. and also the depth that this occurs. So the hydration rim finally, and diffusion depends from the duration, the time, longer the time, bigger the rim, the diffusion coefficient, the ambient temperature, the ambient water and humidity, and chemical structure. The ambient water and humidity, if it is, in temperate climates as usually, and not enough in South Africa, for example, but where I could say from latitudes, geographical latitudes above 35, then from experiments and that have been made, we assume, and it is true, that the habitability is around more than 90%, 90 to 100%. So there is not any induced error because of humidity. But if you are talking about dry climate and Africa, etc., where the humidity is not 90%, it could be 50%, 60%, 70% overall, burial time, then we have to take into account this with making simulation experiments. Otherwise, the errors induced because of the humidity could be 2 or 3 times of the order of magnitude, 2 or 3 times different than the normal age. Here are representative thin sections of obsidian, hydration images from Peru, above. You can see easily, the hydration layer, the rim between these two parallel black lines. Mexico, the same here. Sorry, New Zealand here and Mexico here. Just examples, of the hydrated layer. But in each one has been produced. For example, the A is in the laboratory simulation experiment, experimental aging of 150 degrees for some time, some days. And the second one is 140 degrees, and the Mexican one is 170 degrees. These are the experimental aging in the laboratory in order to reproduce what nature does after thousands of years. But this reinforced hydration in high temperature. Why high? Because in high we can measure in a few days, even 1 month. But if we make aging experiments at low temperature, environmental temperatures, 20, 15, 12 degrees, we need years in order to produce such a hydration phenomenon. That's why we, from the beginning, they started with high temperature experiments and then extrapolate with functional dependence of hydration versus temperature versus hydration depth. They extrapolate to the low temperature, and this is one tricky thing that we have to assume that there is a linear variation, which is not. So in this case, we have to be, to devise anyway other methods, which I will show you later in the dating, that involves, low temperature experiments together with high, and then to use the fitting between high temperature data and low temperature data, temperature against diffusion coefficient or against depth, in order to be more accurate, for applying the dating method at the environmental conditions temperature. Here is another diffusion of water to obsidian. And here is how the SIMS works. As I told you, bombardment with cesium or other ions of the surface of the smooth surface of the obsidian, and then we get this S-like curve, which we can use it for producing the age. This is in a better, higher scale. Let's see. So concentration is a function of depth. Concentration is here. atoms per cubic centimeter. The dating is based on the concentration of hydrogen in water as a function of depth. Later, as I said in the beginning, the hydration layer measured by IR infrared photoacoustic spectrometry. So these are the two peaks, of interest, here and here. 1500 something here, wave number, and here is 2200 something like that. 3,460 represents the combination of hydroxyl with the water bath, and the 1630 peak represents only the water, and this has been measured, and several colleagues have worked since the 1980 decade, until now. Especially the last 10 years, Chris Stevenson from Commonwealth University in Virginia is using, this kind of method to measure, the water, the hydration water with using FTIR pass. Another direction for the Obsidian studies, which I developed last 2 years, is what about if we measure in the hydration layer, if we divide the hydration layer into sub-layers, sub-belts, and we try to see what is the fractal number, an algorithm that characterizes the structure of the image. It is an image analysis, So we had two archaeological samples from a cave from Africa, with a quite large hydration layer. You can see here, late Stone Age dating, approximately. The rim is about 43 microns. Because of high temperature in Africa, high temperature means, gives a greater speed somehow, diffusion rate into this obsidian, which means the water runs faster into the depth of the obsidian and produces a higher rim rather than a lower if temperature was less. So this work, it was an initiative that needs to be further worked out in order to find to define exactly, the front, the end of the obsidian of the hydration rim, and by using fractals. What is here is various parts, the blue or the red, various parts of belts of the hydration and the non-hydration part of the obsidian, which we analyzed by applying certain fractal metrics. Here we have divided the hydration and the unaltered glass, into sub-belts in order to identify with accuracy the end point, the tail of the hydration layer. You can see here very interesting results for the fractal determination of tail of the hydration layer. You can see here using, for example, circularity, one of the fractal indices. You can see how the fractal dimension varies as a function of depth, and you can see here the smaller dimension starts to be the end, the tail of the hydration layer, and then starts the green, the unaltered glass, which is the pristine water that goes in obsidian before hydration, and the circularity in the other obsidian, two obsidians we had from the same tail, also gave the same result. Very interesting. You can define the hydration layer with fractals if you have an image from microscope. and then you apply fractals. You don't need any other device. You can calculate, the calibration layer. Here is also more division of subbelts. And here also we have another indexed Kolmogorov, normalized Kolmogorov complexity, which still, and here even appears, we can define the end of detail of the hydration and local also fractional dimension prediction, complexity, local complexity. This is another index. Again, here you can see, how we can define this layer. This is very recent, and we can actually work eventually in a nanoscale, and probably that has a very promising future for various parameters one wishes to see, in our Obsidian sample. Now, the dating methods. The Obsidian hydration methods, it's the empirical, it is used. Empirical means not based on a scientific basis, but on an empirical basis, but trial and error. And that is the symbol H. X is the rim, the depth in microns, the hydration layer. T is the time, and K is the diffusion rate, which has to be calculated. But with how we can measure X today, we can simulate hydration experiments in the lab in order to calculate K, and then we find it out, the time. So the internal K from induced experiments from 90 to 200 degrees, but the extrapolation to environmental temperature is not always safe. Assuming that it should be, the same functional dependence as it is in high temperature, will be in the low temperature. And so they use the Arrhenius plot, and or they can use the X from the length of the microscope of the hydration layer from the microscope images, or by IR photoacoustic spectrometry. There is an attempt in Oak Ridge, my colleague Ioannis et al. Using the curve, the S-like curve of SIMS profile, applying finite elements approach, but it needs a lot of iterations and having constrained ages dated by C14. So it's indirectly depends from C14. And our method, as I mentioned before, the SIMS-SS, the saturation layer with hydrogen profile modeling using the second law of Fick is a phenomenological approach, not still scientific, but anyway, it is one step advanced than the empirical, because we're using, equations and mathematical meanings, and fittings of real experiments in the laboratory, and according to the physical laws. That's why it is called phenomenological, and I will tell you in which point it lacks, to be completely scientific. So the old method, the empirical, the age calculation is calculated by the measuring the hydration depth, as I explained before, diffusion depth X, K is diffusion coefficient, and the time. As I was talking with Joseph before, for majority of chronological science worldwide, the Obsidian artifact experiences around 100% relative humidity during its burial history, which means that does not produce any problem in the age, except if we are talking about very dry regions, or variable amount of humidity. There, the method cannot be applied, because the humidity is an uncertain factor that induces, unfortunately, serious errors in the age. So we try to get rid from environmental factors. That is the aim of the obsidian dating. Until then, we make various satisfactory work. We make some developments of the existing one, of the classical one. This one, I mean, this. Some improvements which work well. So here, for the classical or traditional method with this simple power law equation, the age depends on the diffusion rate K, which diffusion rate is a function of the temperature, and the G, of course, and the hydration rate. So here we use the Arrhenius plot, which is the index. Well, you can understand this. This is the parallel logarithm of diffusion rate against inverse temperature. Okay, and we get this kind of data. But what is this data? We're talking about New Zealand obsidian. The water in this New Zealand is 0.2% of water, and the high temperature, 5 high temperature data are experimental aging in the laboratory. I mean, at 140, 150, 160, 170, 180 degrees centigrade, for say 20 days, some months, So for the same period anyway. And then we extrapolate this line to the lower temperature for some certain low temperature data in order to get the K. And this is the extrapolation of this data to lower temperature that we're using in order to replace in the age equation into the K, which K depends from temperature. Temperature is measured by an equation which takes into account the last 10 years or 20 years data from the site. And this is not the air temperature or soil temperature, but takes into account also the humidity. So it is called effective hydration temperature, EHT, which combines both temperature and humidity. And this is used as temperature, which we take this temperature from this curve and we calculate the K. And then from the age, knowing the X, knowing the K, for the temperature has been calculated for the present time and in the past, etc. We calculate it after this the time. So this is how most up to now scientists work. But as I said, the calculated diffusion coefficient from artificial hydration, experimental aging in the laboratory, does not secure extrapolation, as I said before. Then a power law, which is in the power of 2, some scientists they have found 0.5, 0.7. They play, with the power in the age equation. The effective hydration temperature also it's very sensitive to the age, plus minus 1 degrees. The age varies between 10 to 13 degrees percent, or plus minus 2 degrees in temperature gives 25% error in the age. So the archaeologists are not so much satisfied, of this approach. And if we have 3% error, we have 37% age. So because of this highly sensitive dependence of diffusion rate to the temperature, as well as, of course, matrix, diffusion species, etc., modifiers also of obsidian hydration rate but all these, parameters do not sufficiently give a precise prediction of diffusion rate. So it is unable to describe the complexity of the diffusion process, and early optical readings are problematic because of the Baker line. We cannot exactly pinpoint where is the end, the tail that stops, the hydration layer. There are some uncertainties in this level. And the relative humidity, as I said, small effect if it is within 90 to 100%. And the most reported ages are compared with other dating means like C14 or sometimes luminescence if it is a cell there. So this is the oral chromatism in a very laser, case. So this is the case how the limitations and the problems so far with this method, which is called empirical, the simple empirical method which is this one. Now, a new development of the empirical dating method has been made as follows. It's a novel approach to the existing one. It was published this year in anthropological and ecological, no, last year, sciences. We used aging experiments from high temperatures, 140 or 50 or 70, within, say, the same time anyway. So, and then we used low temperature experiments that they were made by my colleague Ambrose, William Ambrose from Australia, when he was a PhD student. Now he's 90 years old. When he was a PhD student, he was doing in Australia student dating, and he decided to put in a tank, of 10, 20, 30, and 40 degrees centigrade temperature, obsidians, the same source, until, he becomes, 40 years old, 45. So when he became 45 years old, he was a student then. After 25 years, he was able, because 25 years is enough to make, to develop the hydration and to measure it with SIMS, because with optical means it was difficult even at that time. So because of the development in the field and the use of SIMS, for short period of times, these very, very small hydration layers can be recorded by SIMS if it is 20 years old. And that is very important because then we had low temperature, which is environmental temperature. We find in archaeological sites experiment, conditions like in nature, and this resembles much more what is going on in the high temperature environmental temperatures diffusion rate in obsidians, rather than getting this low temperature value average of the site being extrapolated from high temperature experiments. Well, I have explained to you about the effective temperature, which takes into account end temperature and hydration, and has been developed by Alexander Rogers. Knowing the meteorological data of the site, humidities, etc., and making an equation that is used by most workers. And the general rule is that 100% relative humidity is most context, belt context. Now, what we have done in the one step forward method of the traditional in 1960-63 empirical method is we used low temperature experiments, 10 to 40 data from New Guinea, the experiments that my colleague Ambrose has done, as I explained to you, and also and water between 0.1 and 0.2 percentage, because it's a function of water. The hydration and diffusion rate depends on the amount of water per each obsidian, the pristine water, the water that was there since it was cooled down and made a glass, you know, the obsidian. So the low temperature age data coupled with high temperature data produces a family curve for 3 parameters: LNK, the Neperian logarithm of diffusion coefficient, the temperature in Kelvin, and the water. The water, I mean, the pristine water which characterizes the obsidian. So we used Arrhenius plot, I mean, the usual procedure, but the data are different this time. Not data extrapolated from high temperature experiments to low temperature environmental conditions, but using low temperature experiment and low temperature data from experimental data. And we have found 2 equations, one and second, which the one is for 0.1 around percentage of water, and the second one is for 0.2% of water. You can see everything is similar apart from this parameter here, this coefficient. So this coefficient in the plot of LNK versus temperature, and using the Arrhenius equation, which has also the activation energy, and we have found that there is a dependence between activation energy of Arrhenius plot, Arrhenius equation, and water presence. This is very important. So we replaced the activation energy with the water which has been measured for each obsidian. That's why we produce new different equations here. For the high and for the low temperature percentage of water. So we have used these equations on well-dated samples, of course. This is what we do first. Well-dated not only by the old Obsidian method, but by C14 as well, in the context. And we have got very, very satisfactory results, which validates the concept that indeed the age equation must take into account the water content of the obsidian. And to find the linear relationship, or seems linear, between water content and activation energy. The protocol steps that everybody can use, you know, in his own lab is described here with our new, somehow, one step forward procedure of the empirical dating method. This is the steps I have told you. For example, take the LNK, which is the Neperian logarithm of diffusion rate from the age data. Experimentally aged means in the laboratory. Plot this versus 1 by t and get the slope m of linear equation, and then the slope m, it is activation energy over r, where r is the universal constant gas. You can see here the activation energy is these units, kilojoules per mole. Then plot the water which we measure of the obsidian versus energy, the activation energy, and replace the energy with water. So we get the equation that I showed you before. And then the K is calculated in a more sophisticated way and can be replaced here in order to find the time. These are the 4 low temperature experiments made in Australia by Ambrose for 20 years, as I told you. And these are the Sims profiles, very nice profiles. The one is for 10 degrees, 20 degrees, 30 degrees, 40 degrees centigrade. For the same period of time, you can see how it develops the S-like curve by Sims. And that was, it is centimeters. Here is almost 1 micros, here is less than micros. So it is 52, 52.15, 15, 15, 15, 11. This is the years. 1, 2, 3, 4, or 10, 20. It was not 20, it was 15 years. I was mistaken. So the empirical now dating steps again take into account the water of its obsidian. We use the Arrhenius plot again. The LNK versus T, but the LNK versus T. Sorry, this must be okay. It is calculated using the water presence of its obsidian. In this case here, we used 1, 2, 3 obsidian sources. One BH comes from Body Hill in California, America. Is Liang source obsidian from New Guinea. And Wek comes from Wekok, another source obsidian in Polynesia, in New Guinea. And this is the equation we obtained. And using also the slope which has to do with energy, we make a plot between energy and water, and we take reading of energy, and we have only water present. So obsidian source data, new concept, using all data for the 2 obsidian groups. All the data we have are fallen between 0.1, 0.11% water and 0.2 to 0.23%. So we say we have 2 groups of water, and obviously we shall have to find different results. And these are here the data of obsidian sources used, and all the data of temperature, RIM in micrometers, and time. So these are the data we used. We use data of high experimental results, high temperature results from the laboratory, and low experiments, low temperature experiments in the laboratory. So we produce accurate somehow, I could say, linear variations of diffusion rate, K, Neperian logarithm of K, versus temperature, low or high. We are more close and more realistic in using measured, low temperature experiment, low temperature data, which are environmental temperature. One of these temperatures of low temperatures will be picked up, in order to be used for the dating. But so far, the low temperatures were not measured, but they were predicted, extrapolating high temperature to low temperature. That is the new step we have made, that is using low temperature, not predicting from high temperature. Here you can easily see 3 points, while there are a small number of points, but still you can see a linear relation between activation energy and amount of water in the obsidian. If we use more obsidian with water content measured, you can see here something else, another picture. Between near 0, 0.1, say, and 0.9% of water, look here how it varies the activation energy of these obsidians versus the water of obsidians, the water, the crystalline water, the structural water. Here it's not linear, but has a kind of power law, which is here. So if you take only data around here, you may say, okay, this is linear. So one has to take into account also these variations in order to reach a more reliable result. Calibration equation with water. This is for the Body Hill Obsidian, California, America, and this is LNK versus temperature, including predicted low temperature data. Here are the Body Hill 0.25% of water high temperature aging experiment. And here is Body Hill, New Zealand, Mexico, predicted data for low temperature for 0.2%, all of them. You can see actually some family curves, as I mentioned earlier, that they follow this kind of line. And this is another point that one has to develop further and to identify these family curves per sample and per case of water and water presence in this samples. Here is all samples LNK versus T, and you can see easier the family curves of the linear variation between LNK and TERS. So for low water data, the LNK versus T for high and low data, it is here shown. These are data measured, not predicted, and the energy is about 90,000 joule per mole. So the new age equations are based on K and T and water. Okay? And these are the ones for low water and for high water. And the only difference is this coefficient here. Always based on the traditional empirical age equation. We have made some comparisons of what was before, what is with the new little advancement of the dating method, the results in age. On the left side, you can see ages made by Chris Stevenson, computed rate by Rogers and Stevenson, and their model. So the red is the age by them, the red. The green is our results with low water percentage, and the other, the blue and the green is the age using three data of water. Anyway, if you can see the comparison, in some cases there are some variations, and this comes from Xaltocan series of dates as a function of depth. There are some, in some cases here, for example, probably here too, and here that we have differences between the earlier age calculated by Rogers and Stevenson and with our ages calculated based on the new low temperature data, which are measured and not predicted. Here also is a comparison reported by dates by C14 and other methods. In Papua Island, Napa Valley in California, Shirataki in Japan, OCH Japan, Easter Island in red, and with present equations that I showed you before. So you can see here comparison data by author is the red one. The green is by hours low temperature water. The brown is by Stevenson, the earlier dating equation. So you can see the comparison here, which are not bad anyway. The LNK versus temperature for different combinations of sources, you can see here. Because if you take LNK, you understand with the temperature for one source, it could be good, to have a universal equation. So we use various sources, the data we have. For example, here the samples are from Peru and Umland, from Giguni, or Peru and Huecoc. Huecoc and Umland are the sources with low temperature measured experiments, temperature. And pH, which is the California, etc. And you can see the slope, the latitude, the LNA, and the water. In each case, and the slope is calculated on average. This one here, and the LNA is 31.44. So in conclusion, we obtain family curves for different water content and age data. The latter is due to the mechanical and chemical characteristics of each obsidian source. The present investigation verifies the much wanted calibration equation, which is not an easy task. The use of long-term of low-temperature experiments reflects archaeoenvironmental, chemical, and structural conditions. And the Arrhenius plot also is using present data, indicates very extremely sensitive change to EHT, effective radiation temperature, but also the crystalline water. And the pre-exponential term A, the rate and imperial temperature, depends on the obsidian sources. So from this first reaction of the developed method of empirical dating, we can say that, for example, if we are going to date the samples from the Aegean Sea, okay, that the main source is Milos, we have to make low and high temperature aging experiments for Milos samples, and to use this equation to date any artifact which is found around the Aegean and beyond, which comes, we can find it easily, from Milos Island or from Ialik or from Adiparos. The same applies to the Italian sources in central Mediterranean. So it is somehow on average a universal law, but for accuracy, we have to concentrate on the source, on a particular source that the artifact comes from. Now, the SIMS SS dated method now is the phenomenological method. The other one, which I was talking to you, which really it is a very great advancement, but we need not only a microscope to make thin sections, but we have SIMS, secondary mass spectrometry, in order to make the curve, the profile of water through hydrogen plus as a function of depth. This is, I showed you before how it works. So once we get the data, this curve, then we have to manipulate somehow the data and to characterize the appropriate equation according to the physical laws of diffusion and to derive the age. So the new dating approach is different from the solution of difference. It is derived from a solution of differential equation that describe the diffusion process. It's well known in books like Crank, 1975 from Oxford. It is based on the modeling of water contribution into the Obsidian, the modeling of this water. The water distribution is measured with the SIMS, and we have a concept of surface saturation layer. This layer is created in the first around 1 microns of the Obsidian surface due to the different speed of water and into the Obsidian, and we have seen from this curve that we gave, the S-like curve, that there are two mechanisms, the region 1 and the region 2. The region 2 is best described by Fick's equation, Fick's second law of diffusion. And the first one is somehow exponentially decreased. So we have to bridge these two regions to make one fitting equation, taking into account the physical laws in order to deduce from this fitting the time. Somehow approaching this SIMS technique, because they tried in Oak Ridge, Tennessee team, they were called ODD SIMS, Obsidian diffusion dating by SIMS, something like that. But it was entirely dependent on constraint points via C14, so it was left, it didn't go any further. Because the SIMS SS seems independent of such calibration. So the concept is, as I said, the surface saturation when diffusion starts. Within a small period of time, there is this saturation layer. This median time with respect to Obsidian age is taken as 0 for us in the calculations. The concentration is constant, and in this surface saturation layer, starting point for further diffusion starts from this point. This is the concept, and for future environmental conditions, for natural environmental conditions, the boundaries and burial depth and any variations in diffusion is insignificant. That is very, very, very important. And also any peeling effect is insignificant, less than 1 microns anyway. So we have various, you can see here various SIMS profiles, and you can see here the surface saturation, somewhere here appears, and here also other examples from WECOC source of 10, 20, 30 degrees. You can see somewhere here is the surface saturation layer that we define by iterative procedures mathematically. We define this layer that has slope 0, You can see once more this layer is there. And then what we do is we model the form of diffusion profiles according to the Crank 75 theoretical curves, were consulted, of course. We made various curves, theoretical curves, which resemble to the experimental one, and the boundary conditions is that the concentration, initial concentration of internal crystalline water at 0 time is CO, and then it eventually reaches the concentration in the surface, which is called CS. We can measure this in the curve, of course. And then the saturated layer depth is called XS from saturation. And the surface saturation layer is the average of all, whatever we see in this curve, finally today by seams, includes all environmental conditions during burial time and the burial site. So we do not need to know average temperature and humidity and everything else. Whatever it happened during the burial time in this artifact, it is recorded by this final S-like curve, which is defined, measured by seams. So by working out, various parameters regarding the surface saturation layer, the concentration, the etc., we fit, make a fit of polynomial fitting of the seams curve. We define the SS layer, as I say, by iterative procedures. It is the part of the curve that is sloping zero. And using Boltzmann and Crack solutions, and Boltzmann for certain boundary conditions, of course, in fixed equation, which is converted to a simple differential equation, then we can say that we have useful points in the novel dating method. The useful points concern the non-dimensional plots of concentration versus depth in certain exponential coefficients. These are finally the equations that we produce from Fick's law and other equations that briefly, I passed by. So you start finally what we reach. And this is exponential concentration as a function of depth of this type of the S-like curve, and the diffusion coefficient is defined as the first derivative of fitted curve as this one here. So then we have to define surface saturation layers, which is the concentration at the surface saturation and the depth at the surface saturation, using the third order polynomial, best fit and tail effect. We find the derivative, and finally we can find the steps that get to the H. First, we have to convert the atoms per cc to micrometers, and to centimeters, and grammole per cc. This has been made anyway in a software which gives the age, but requires various data to calculate. And then here we have found that the diffusion coefficient does not give good ages, because for some reason, which it is the weak point of the method, that we call it phenomenological, not exactly scientific. It gives good data only if we calculate the diffusion rate as a function of well-dated samples where we know the diffusion. And then we make an effective diffusion, which has to do with the empirical one. So we don't know yet how to overcome this problem, but this empirical parameter makes our system phenomenological and not exactly scientific. We calculate the internal concentration of water very easily in the unaltered part of the obsidian. And the H equation finally comes here, where the C and Ci and Ss are measured in the concentration layer in the internal part of obsidian, and the K is calculated from theoretical curves of Crank, from theoretical curves, Si, Ss, and this empirical effective diffusion coefficient with A and B well known, and then we calculate the age. That is, this is a software for all this, mathematical processing that I was telling you, and also the saturation layer can be easily calculated by fitting and taking the first and second derivative of this curve. So these derivatives, they define the surface saturation layer as an inflection point to the second peak, and linear regressions. So the definition of SS layer is another procedure which, as I said, easily can be calculated. For example, here it is exactly there. We know in this length of depth in the 50 or 55 channel or 60 channel, exactly there, which corresponds to a certain hydration depth. It is the depth of the surface saturation depth. And for example, here is a very good example that we have expanded, zooming, a part of this curve here, and you can see a little part of the curve that is flat. That means has slope 0. So for us, the average of this part, column number, gives the saturation depth and the corresponding, of course, concentration value here. And we have developed actually some parabolas in order to, for example, if we have this SIMS profiles for the same sample from Jura, is an island cave in an island in Greece. These are fittings with third order polynomial. But what we did, we cut some points at the end. You can see here the tail is bigger, here is less, to see if we cut some points at the end, the overall calculation of third polynomial, order polynomial, affects the final equation. And we have found criteria that how many points at the tail have to be cut in order to be precise in the dating. And we have produced finally parabolas of this kind of fitting square root fitting of various polynomials by cutting various number of points at the tail, and we have produced such parabolas which indicate the top here, the peak or the trough exactly here, the saturation level. It's very important to this concept of saturation level to be absolutely defined as X, where exactly it is and with how many microns, and exactly what is the concentration. And also the K, which is a parameter in the age equation. As I said before, but here I can repeat, we can calculate theoretical curves, and the K is measured here. We take the curve which is more close to our curve, and this curve has an EK number, exponential to the K equal number. This is the K that we use in our equation. Okay, the same theoretical curves and actual curves. For example, here the surface saturation is this curve. This SIMS curve resembles to this one here. We can make comparison, cross-validation, of course. And this curve, green here, has E in the K exponential in the power of K, 80. So we use this number for the dating of this sample. Other times could be this number here, 140. it is very precisely mathematical development, or with only one drop, in this whole procedure of which concerns the diffusion coefficient must be an effective one, but based on available data. Okay, I don't want to get into more to this because we have said that many times. So this is the final age equation for the Sims SFS dating. And I'm looking forward to have a Sims instrument in order to proceed more with dating samples, for overall the world using this equation. Here you can see various shapes of hydration of water measured by Sims as a function of depth from various samples. There is also some limitations, change of the age in green for change of 2 plus 2 plus minus 2% and plus minus 10% of respective variables here. You can see the respective percentage in age equation. Here, the change of age by 10, minus 10 to plus 10% of the how the age varies, by plus minus 10% change in the parameters measured, which is the saturation layer and the saturation concentration and the effective diffusion rate and decay for an age of 5,680 BP. Probably it's difficult to see here, but you can see the change of for example, here, percentage of change of X saturation, the layer that we define, saturation layer. If it is 2% or 4%, then you can see here the age. Instead of 5,680, you can get 5,500, etc. You can see here a comparison between archaeological ages and Sims SS ages from different parts of Asia Minor, Greece, Mexico, Hungary, Japan, etc. These are the archaeological ages, and these are the Sims SS ages. So, and this is the comparison as a plot, the archaeological age and the Sims SS age. So that is shortly. I would like to tell you that I have found a power law of temperature versus depth versus hydration layer, which is gives somehow interesting results. I mean, if we get pixels, the image, pixels per year or micros per year, and you have from an image the depth of microns or the pixels, simply transferring, or converting the pixels you have the unknown age of an artifact into pixels per year or micros per year that we have calculated for the same obsidian, but from experimental aging experiments. We try to see if we can use, this kind of simple power law, which has an exponent of 3.2 to 4, the exponent, of hydration area of pixels versus temperature, or depth per year versus temperature. It is interesting to see that we have got some very satisfactory data compared to the well-known ages. This is something else that we have developed from various parts of the world, the Napa Valley, from this simple power law. this is the power law that we used, for different sources, Mexico, New Zealand, California, etc. These are always the exponent is around 4, 3.7, 3.9, 3.7. It was very interesting, and we tried to see, if something useful comes out of it, and we got some interesting result. Really, we have compared here, but we are not relying very much on this. It is supplementary somehow, a verification. We want to apply also another approximation to the empirical method. So the power law conclusion is interesting. On average, the exponents are around 3 to 5, and that may give also some input and food of thought for developing a combination of what I presented you, a combination of approaches in order to be more reliable in the age calculations. Thank you.